While I'm getting this set up, you can go ahead and start copying down our example 6 if you haven't done so already. Let's see, that's working fine, perfect. That should be good, but just in case, let me do this. Perfect. All right, so I guess we'll find out if this works based on how the stream turns out. All right, so let's go ahead and continue where we left off. Last time we finished example 5, where we had something like the limit as x approaches 5 of x squared minus 25 over x minus 5. So now we're just going to go ahead and continue where we left off with example 6. Remember last time I said that today, part of it is going to be testing and seeing if we remember some of our algebra skills. So let's start off with part A. Let us take the limit as x approaches 49 of the square root of x minus 7 over x minus 49. So I want to recall what we did a little bit last time. Remember we said for an expression like this, if I can plug in my value and get a nice clean answer, clean being a real number, then we're done. Am I able to just plug in 49 into this expression? Certainly not. Quick reason, I see here if I plug in 49 into the denominator at the bottom, I get 49 minus 49, I get divided by 0. I do want to point something out about this problem though. Not only do I get 0 on the bottom, but I also get 0 on the top. Square root of 49, I have 7. 7 minus 7, I get 0. So in particular, I get 0 divided by 0, which some of you already know is what we call the indeterminate form. This 0 over 0, it actually gives us a hint, and it tells us we may be able to actually do an algebraic manipulation and do some cancellation perhaps to fix this expression. So looking at this, what might I be able to do to clean up this expression square root of x minus 7 over x minus 49? We have two ways that I'm thinking of. Square the whole equation. Well, although it's a good idea with the square root, we want to be careful because if I square the entire expression, then we actually change its essence, the quality. This is not, and in particular, this is not an equation. We don't have one side equal to the other. It's kind of like if I had, for example, square root of 2, and if I square it, it's no longer the same value. So we do have to be careful about that. Any other ideas on what we might be able to do? Bring what down? Oh, break it down. How can we break this down? I'm thinking of two possible methods that might be useful. Not exactly x plus 7, x minus 7, because we don't have an x squared, but that is a good idea on what we could do. So I'm going to show y'all two ways we might approach this algebraically. So the first method, last time, you don't have to write this yet, we had x squared. I hope this doesn't crash, because I spent so much time writing it. Oh, well, that's disappointing. Let me see if I can close this. Well, that's about 30 minutes of writing that I had to redo. Not a problem. Okay, now it's just not working at all. Will you come back? Cancel. Perfect. I don't have to rewrite everything. So you don't have to write this, but how did I break down this from example 5? We knew that this broke down into x minus 5, x plus 5. How did we know that? Let's see. Well, this is a difference of squares. We knew that the square root of x squared, we got x, square root of 25, we got 5. This was a difference of a square minus a square. So I look over here and see x minus 49. 49 is a perfect square. I claim I can do the same thing for x. That is, why not write this? The limit as x approaches 49. What if I leave this the same on the top? I don't change anything. But on the bottom, how about I write this? X minus 7, x plus 7. This is still the same principle. We know square root of x times square root of x, that's x. Just like here, x times x, we have x squared. So this is a hidden difference of squares. Even though we don't usually think of splitting up x, it's still reasonable for us to do. This is one way we might approach it. Why would this be useful for us, what I just wrote? Yeah, I have square root of x minus 7 on the top in my numerator and on the bottom. So I have some cancellation, leaving me with a plain 1 on the top. Remember, whenever I cancel something from the numerator and denominator, it does not mean that everything goes away. I still have a 1, an understood 1. So if I rewrite this, I still have the limit as x approaches 49 of 1 over the square root of x minus plus 7, excuse me, like so. All right, so what can I do from here? We can try to plug it in. I just did some cancellation. Perhaps that gets rid of my problem. So if I try to plug in 49 into this expression, on the top, it's a plain 1. Nothing to talk about. On the bottoms, I plug in 49. What's square root of 49? 7 plus 7, 14. Oops. 1 over 14, that is a nice real number. We're done. This is one way I may have approached this problem. I'm going to show you the second way in just a moment that we may have done this. Does anyone have an idea what's the second way I may have done some algebraic manipulations? How about I bring up this term? Yes, exactly. What if I think about a conjugate? Remember, simply speaking, a conjugate of a binomial is where everything's the same, but I change the middle plus to a minus or vice versa. That is, let me copy this original problem. The second way I might do this is, what if I multiply by the square root of x plus 7 over the square root of x plus 7? I am still allowed to do this because this is times 1. Not any problem. I did not break any rules. The quantity, the essence is still the same. But by doing this, I still have the limit as x approaches 49. On the top, here's why conjugates are quite nice for us. Yes, we can FOIL, but one nice property of a conjugate is square root of x times square root of x. We get x. Negative 7 times positive 7, minus 49. If you did your classic FOIL method, for those of you that are used to it, this would be your first times first. Your outside would be negative square root of 7 times plus positive square root, 7 square roots of 7, x. On the bottom, I'm going to leave it alone for just a moment. We had x minus 49 times square root of x plus 7. What do I know is happening here? We have some nice cancellation. X minus 49, x minus 49. Then I'm left with an understood 1. What this allows us to do is I have 1 over the square root of x plus 7. That's exactly what we had over here. So both of these methods do work out. That is, using the conjugate or breaking down and recognizing that we do have sort of a hidden difference of squares. So either of these methods eventually lead you back here. I will say the first method is not as intuitive for a lot of people because we're used to seeing x squared minus another square. One way or another, we will get 1 over 14. Any questions about this part A? We have 2 methods to get us to the same solution. All right, so once again, notice here the actual calculus portion, we didn't do too much. This was largely 90% algebra work. Now, to further test your algebra skills, let's see if you can do part B, the second example I have here. I'm still going to try to leave most of this up. What if I take the limit as h approaches 0 of the square root of 36 plus h, close the square root, minus 6, all over h? So first step is, can I just plug in h is equal to 0 into here? No, certainly not. Even further, I see if I try to plug in 0 into the top and the bottom, once again, I end up with this indeterminate form, 0 over 0. Again, a little bit of a hint telling me I may be able to do some algebraic manipulations and clean up the expression. So the question now is, what can I even do here? I'll start off by saying I certainly cannot do a difference of squares. Therefore, I'm forced to use one particular method that we used earlier. I'm forced to use our conjugates. Looking at this, suppose I multiply by, I write the exact same thing as my numerator, but instead of a minus, let's change that to a plus. So let's say I write 36 plus h plus 6. Notice I didn't change the square root itself. Plus 6. Once again, very much so emphasizing I am allowed to do this because I am multiplying by 1. I'm not changing the essence of the expression. The quantity is the same. It's just written in a slightly different way. So let's see, what does this become? One thing I'll note about this problem is that it will look like it gets messier before it gets cleaner. And that's something that we will expect for this type of problem. So let's see, how do we multiply this? On the top, again, we specifically chose the conjugate. Multiplying by the conjugate allows us to do this multiplication very quickly. That is the square root of 36 plus h times the square root of the same thing. Well, that gives us simply 36 plus h. Again, if you're thinking about your FOIL method, this is the f. We also have negative 6 times positive 6. What does that give us? Negative 36. And on the bottom, suppose I just leave that alone. Just h times the conjugate. So what I did from this side to this side is I multiplied the numerator, the top. I did not touch the bottom really. I just have h times the conjugate. All right, so why is this really nice for me? Do I notice anything unique occurring here that may be useful? Yeah, let's look at the numerator. I have 36 plus h minus 36. So 36 minus 36, that becomes 0. And then I'm left with a plain h in the top. Is there anything else that I can do that might be useful for me? Yeah, I have h on the top by itself and an h on the bottom. So actually, I get another cancellation there. My first cancellation is because I have 36 minus 36. The other one is cancellation through division, h divided by h. And again, whenever we do some cancellation by division, there's still an understood 1. So let's rewrite what we have. I still have the limit as h approaches 0. On the top, fortunately, everything canceled, and I'm left with a 1. And on the bottom, I still have this almost weird-looking square root. Plus h, was it plus 6? I'll move this up a little bit. Oh, so here we just have 36 minus 36. So 36 minus 36, we just get a 0. Same thing for the h's. We have an h on the top and an h on the bottom. We cancel through division. One mistake I always want to point out is, again, when we cancel through division, it does not mean the top went away. It means that we are left with an understood 1. All right, so I did all of this cancellation, and now I have a new expression. Whenever I look at my original, I know that the h on the bottom was giving me my main issue because we didn't want to divide by 0. Well, we got rid of the h. We got rid of the problem. So now let's try to see what happens if I try to plug in 0 into my expression. Again, if I plug in 0, on the top, there's nothing to do. It's a 1. 36 plus 0, we get 36. What's the square root of 36? And then we get 6 plus 6, or 1/12. So again, this was an algebraic technique in which we applied the conjugate. By multiplying by the conjugate, we were able to manipulate the expression and turn it so that we have some really nice cancellation. Any questions about any of the steps I used for this part B? I'll give you some time to write this down for anyone as needed. One thing I will note is that this particular expression is a little unique. We will see this type of expression, square root of 36 plus h. Well, square root is something plus h minus something all over h. We're going to see this expression again, maybe next week or the week after. We'll actually spend quite some time evaluating expressions such as this. If I were to give it a name, the official name, this is the limit of the difference quotient. Again, the limit of the difference quotient. So this type of problem has a name. Limit of the difference quotient. For those of you that may have taken calculus before or some introductory calculus, you know where this is eventually going to lead in about a week or two. So I'll give you all time to write that down. So there's very many manipulations that we can work with. Again, at this point, we've only dealt with the situations where I can plug it in directly and be done. The second situation is I try to plug it in, but I get 0 over 0. And then that tells me let's try to do some algebra, clean it up, and see from there. One of the situations that we have not encountered yet is what if I can't simplify it? What if, for example, instead of 0 over 0, I get, I don't know, a number like 8 divided by 0? How do I deal with that? So just to be clear, don't write this yet, but we'll talk about what happens if I have this. The limit as x approaches 1 of, I don't know, 4 over x minus 1. Clearly here, I can't do any cancellation. There's not even any algebra that would help us. So this is something that we'll reserve for next week before I move on here. So we now know how to take the limit of algebraic expressions. I want to go on a slight tangent and talk about what if I don't know what my function is? What if I want to be a little bit more broad? That is, what if I have this question? Example 7. Suppose that all I know about my function is I have a lower bound and an upper bound. So I have f. On the lower bound, I have 1 minus x squared over 4. On the upper bound, I have 1 plus x squared over 2. I'll give some time for y'all to copy this down. Given this information, is it possible for me to find the limit of f of x as x approaches 0? Again, I know nothing else about the function f except that this equality must hold. So the question is, how do I even find the limit of the function if I don't even know what the function is? And we can assume that this equality holds for all values of x. So no matter what I plug in, this should hold true. Yeah, and you use a very prime word here, sandwiching these equations together. That's going to be key in a moment. So I have this inequality. It must hold. So one of the rules we learned in algebra is if I have an inequality or an equation, if I apply it to one portion, I had to apply it to all parts of my equation. In other words, here's f of x. I want the limit as x approaches 0 of my function. This is what I want. Well, I can do the same thing to the left and to the right. That is, what's stopping me, if anything, from writing this? 1 minus x squared over 4. I maintain the inequality. And then the same thing on the right. What is this? 1 plus x squared over 2. Like so. I haven't broken any rules. My inequality still holds. It almost looks like I applied a limit to all three portions in a sense. So let's see, why is this useful? Again, I want this middle portion. That's my end goal. Let's look at the left. What is the limit of 1 minus x squared over 4? What is this limit going to be? 1, because again, we can try, can I plug in 0? 0 squared, I get 0. 0 over 4, 0. So 1 minus 0, all of this becomes 1. I still have less than or equal than the limit as x approaches 0 of my function. What's the limit on the right side? The limit of 1 plus x squared over 2. It's also 1. Again, I can plug in 0 very quickly. 0 squared over 2, 0. 1 plus 0, I get 1. So I know that my limit must be in between 1 and 1. Therefore, what can I say about my limit of f of x? Yes, the only way for this inequality to still be true is if my limit itself is equal to 1. The limit as x approaches 0 of my function is 1. In other words, I had an upper and lower bound. By taking the limits of all my expressions, I was able to actually sandwich or squeeze my limit between these two values, which happen to be the exact same value, in order to keep the inequality true, because all this still has to be true. There's only one possibility. That is, it has to equal 1. Because clearly we can't make a number that is bigger than 1 and smaller than 1 at the same time. So we're left with equality. All right, so what I did here was I'm going to lead into our next theorem. But before I do that, any questions about this example? Let me zoom out for anyone that wants to see the whole thing. I think I still see a couple of pencils, so I'll let y'all write. I understand how outside the one, but how the limit of. Yes. So do you agree that my number has to be between 1 and 1? Can you think of a number besides 1 that's in between them? So here's my number line. Here's 1. You want to be bigger than 1, but also smaller than 1. There's no other number except 1 itself, which is why we also have this equal symbol. We only have one possibility. Is it ever possible for it to be less than greater than without being equal to? Yes, so good question. In this case, no. If I do not have the equal sign, then we have no chance. Because, for example, let's say this was gone. Then I would have to erase the equal sign here and the equal sign all the way down. And then we go back to the question, is there a number that's bigger than 1, but also smaller than 1, but not equal? Then there's no other options. In other words, that equal sign was necessary for us. If you see not an equal sign, then there would be no solution here. Or, yes, no solution. So again, using that word, we squeezed the limit or the limit of our function out from the upper and lower bounds. And I'm using the word squeeze and sandwich because that will actually be the name of our theorem. So, theorem statement. This is going to be called the squeeze, or some places call it the sandwich theorem. So what does the squeeze theorem state? The squeeze theorem states, suppose we have 3 functions in this order. Suppose that g of x is less than or equal than f of x, which is less than or equal than h of x. So I have an compound inequality, just like what we had in the previous example. If we have at the limit as x approaches, let's use a here, of g of x, so the limit of the lower bound is also equal to the limit of the upper bound. Let's just call it some number L. Then we can make the following conclusion. We can conclude that the limit as x approaches a of my middle function is also the same value. So just like before in the example, we said the bottom limit is 1, top limit is 1. Therefore, the middle limit also has to be the same number, 1. This is what the squeeze/sandwich theorem is stating. For which part? Under the limit. So this one will be an A. Usually for my Q's, you see me denote it this way with a little line. Good question, though. Any questions about this squeeze/sandwich theorem that I have? I want you to put a star next to this theorem because we may apply it in the future, or I may ask you to state this theorem in the future. We won't prove this because the statement itself is a little bit straightforward in the proof. So now that we have the squeeze theorem, we're going to go ahead and do an application of it. Well, not an application, but we're going to do another example. In this next example, I'm going to say, for the previous example, I gave you the upper and lower bounds. I'm going to give you an example where I'm not going to give you the bounds in the initial problem. I'm going to ask you to find an upper and lower bound on the function. That is example 8. Suppose I want the limit as x approaches 0 of x squared times sine of 1 over x. So this is our first trig function that we've seen so far. And I claim we can't plug in 0. Why can't I plug in 0 right away? Yeah, we see a 1 over x. I don't want to divide by 0. There's a long story short. Even if it's in the sine function. So I'm going to have to get a little bit creative here, in particular with my sine function. Does anyone remember anything about the sine function? In particular, any upper or lower bounds on sine? 1 and 0? So in particular, we know that the sine function from trig, if we were to graph it, it looks something like this, right? It goes up and down, oscillates. It has a natural upper bound and a natural lower bound, which we happen to remember is -1 to 1. In other words, I'm going to do some scratch work here. We know that sine is always between 1 and -1. This is a fact here. Does it matter what x is in this case? Is it possible for me to do sine of anything else and get something bigger than 1? Well, based off our graph, no. So I'm going to make the further claim here that this is still true. Because it doesn't really matter what's inside of my sine function. Sine of anything is always still small, between -1 and 1. Be bigger than 1 because our x is squared and it's being multiplied by sine. So we're going to get there in just a second, because right now we just have sine of 1 over x. So good point here. I'm very close to what I have in the beginning. So let's just multiply by x squared. If I multiply the 3 parts by x squared, can't I still have this? Negative x squared is less than or equal than x squared sine 1 over x, which is less than or equal than x squared. This inequality must hold because I multiplied the whole line by x squared. I want to take a pause here. Why would this problem not work if it was x sine of 1 over x? Well, maybe not why will it not work, but what issue might I have? What if instead of x squared in the beginning, I just had x sine of 1 over x? What issue might I have? Could be 0. And what happens whenever I multiply an inequality by potentially a negative number? You would have to flip your inequality, right? It's kind of like whenever you do, we agree that -1 is smaller than 2. If I multiply it by -1 again, we'd have 1 is greater than -2. So if this was a plain x, I don't know if I'm necessarily working with a positive x or a negative x. I don't have to worry about this for x squared. Why do I not need to worry about negative numbers for x squared? X squared will never be negative for our real numbers. Again, we're not going to talk about the imaginary numbers or complex numbers. So this inequality should always hold no matter what x is, because we're squaring it. I'm just multiplying by some positive value. All right, so we're almost done with this problem. What do you think I should do next to continue from here? Square root it? Do we need to take a square root? Remember, our end goal is finding the limit of x squared sine of 1 over x. So first off, do we have x squared sine of 1 over x on here already? Yes. So that means I'm not going to do any more multiplying. I'm not going to be touching my inequality, strictly speaking. But I can apply the limit. Or another way I can write this is true. What's the limit of the left? 0. What's the limit of the right side? 0. In other words, I could write this. The limit as x approaches 0 of the left side. We don't have to write this necessarily, but just for notes, what's this? X squared sine of 1 over x is less than or equal than the limit as x approaches 0 of x squared. Ugly x. So y'all told me the limit of the left is 0. What about the right side? 0. So the bottom limit is 0. The top limit is 0. What must that mean for our middle limit? It's also going to be 0. So once again, we found the limit of the upper bound, the limit of the lower bound, and they were the same number. Since they are the same number, I must have that the middle value is also 0. That is, therefore, I'm going to be a little bit lazy with this. The only way for this to work is if we have 0 here. So my limit must be 0.
So for the inequalities, will they be specified to have like if they're real numbers or not? Like,
For our entire class, we will only assume we have real numbers. For our class, we will never deal with the complex imaginary numbers. Mainly because even though it's not in the name, Cal 1 through 3 is typically actually called calculus of real variable functions. I always tell my students the complex variable, there is a whole calculus about that, but then that's mainly used by people who are going into physics, especially if they're looking into some quantum mechanics and other quantum computing and stuff like that. All right, so this one, even though I did not give you upper and lower bounds, the sine function has some natural upper and lower bounds that we could have derived. The other note I'll make here is that the squeeze theorem only works if the lower and upper limits are the same. Let's say that this was 1 and then this one was 0 somehow. There's nothing else I can really do there. It has to be both the same value for me to make any other conclusions. So that's a small note about what I have here. Any questions about applications of the squeeze theorem? If I want to be exact about this picture, I'm not going to give you the most accurate one. Let me see if I can make this really tiny and draw something. Oops. This graph will actually look like this. What does x squared look like if I try to graph it?
It'll be,
We know that x squared, that's a parabola. It's a U-shaped graph.
oh, it's like,
So this is x squared. What about negative x squared?
look down.
Yeah, it's the same thing, but just flipped upside down. Oops, let me make that a little closer. Again, not to scale. So I have my upper bound and lower bound. Look at what's happening whenever x is getting closer to 0. I have to squeeze through this tiny little portion in between the two functions. The graph of x squared sine of 1 over x actually looks something like this, if I were telling you to graph it, if I remember correctly. That's a graph of the middle function. Again, not necessarily to scale, but it's an oscillating function. Question? So it looks something like this, a very big complicated function, but it gets squeezed through these two regular quadratic functions. It's because of that little squeeze or little hole between the two that we're actually able to evaluate the limit of this expression. You can imagine if I just gave you this graph and said, give me the limit, then it might be a little ambiguous. All right, so that is the graph of x squared sine of 1 over x. And I believe that's all the time we have for today. Besides that, I'll go ahead and see y'all tomorrow. And then hopefully this live stream was able to be recorded with the proper audio. So I'll go ahead and check that out.